Hello, James. How are we?
Hello, how I'm good. How are you?
Good.
That's good.
Jan.
Hey, hi Glenn, hi James, hi everyone. You tell me
Um,
when are we starting?
we start soon,
Okay,
and maybe we give it a couple minutes, and then we end at 11:30. I have to. Maybe I'll stop talking at like 11:25 so that we have some time for questions.
okay.
Hey Glen,
Hey, Stepan, how you going?
good. How are you?
Good. Um, I got a bit carried away writing slides. So let me see if I can share my screen. And last time in my last seminar, I had terrible technical difficulty. My thing didn't work, and so Matt like helped me by annotating on the slides while I was talking. So I got a new program. Okay, it works. So that's good. Um, but yeah, I got a bit carried away. I wrote um, 78 slides. So maybe I'll have to go for another hour. So I'll probably just do three seminars. Um, I don't think I'll get through all of it today. So it just means that after me, it'll be, well, maybe I should talk about that when we're recording. Oh, it is recording already?
It seems like it is.
No. Um, okay, whatever. So yeah, so then after me, Devesh talk about Leon Simon's existence of Willmore surfaces, and then Jan, you have agreed to give a talk.
Yes, I've agreed to give a talk. It probably will be two because we'll do the regularity of weak solutions of the Willmore energy, critical points of Willmore energy. So this is going to take probably, yes, 2 hours, I would say.
Cool, awesome. Thank you so much.
Sure.
Um,
Should we start, Glenn?
yeah, let's start.
All right. Well, welcome everyone to this new edition of the seminar series, and Glenn is going to continue to tell us about the Willmore energy, the Willmore flow, Willmore surfaces, all things Willmore today.
Thank you, Jan, and thanks everyone for coming along. Today, I'm actually going to be focusing on one paper basically, and I'm extremely lucky that Jan is here because a lot of the things that I learned about this paper I learned from Jan. So if I make any kinds of mistakes or anything anything embarrassing, please save me, Jan.
I will. I'll do my best at least.
Okay, thank you. Awesome. So what are we talking about? All right. So this is the second seminar. It's got a star here because it might turn into um, maybe two more seminars. I guess it depends on how fast I go and how much detail we go into. But yeah, the idea is in this seminar we'll talk about Bryant's paper in JDG from 1984, which is a duality theorem. He calls it a duality theorem, but there's theorems A, B, C, D, and E in that paper, and we're going to talk a little bit about all of them. And it's very computationally heavy, so we'll see how we go. I'm going to explain all of these things in more detail. So this is just a summary. You're not supposed to understand it straight away unless you've already seen this stuff, and then I don't know, then you can go to sleep. But there's a thing called Lorentz. So there's the Lorentz model, which is basically a way of highlighting the existence of a second surface from a given surface, which is a very general construction that leads to this object called the conformal Gauss map. Using this conformal Gauss map, we can construct this second, it's a second envelope of mean curvature spheres, which is called the Bryant dual. And then all of this theory gets applied in a really dramatic way to what we call Willmore spheres, which are just when the domain is a sphere. So you have this immersion that can be Willmore. Being Willmore it's a local property, right? So any neighborhood of a point could be Willmore by just satisfying the Euler-Lagrange equation for the Willmore energy. So it doesn't have anything really a priori to do with topology. But when the topology does enter the picture, when you do know that you are on a sphere, then some rigidity applies. And Bryant's theory, which involves, very importantly, this quartic differential, gives you a classification result, but it does take quite a bit more work. Anyway, and that classification result gives you a energy estimate, which is what enters into the analysis of the flow. The flow part is just 10 slides, so it doesn't take very long. I might not get to it, but essentially what happens along the flow, this is Kuvert and Schätzler's contribution. The whole thing is, so you take the gradient flow of the Willmore energy in L2 with the induced measure, L2 d mu, and you can show using an adaptation of Struve's concentration compactness for harmonic map heat flow, which is what Kuvert and Schätzler adapted to the Willmore flow very nicely, that when there's a finite time or long time curvature singularity for the flow, there's a sequence of space and time points and radii along which the curvature must be quantized. So it can't disappear. It has to be constant. So you rescale and you produce this limiting object called a blow-up limit. And that blow-up limit, because of the scale invariance of the Willmore energy, is going to be Willmore again. And so then you produce this Willmore surface. And then at this moment, this is really when Bryant's result applies. So I will talk in more detail. So in this slide deck, there's 10 slides on this, so it's not much. Once we go through Devesh and Jan, then I'll come back to the flow and I'll do all the details of this series of implications. It's a pretty long story, and it's one that I'm very familiar with. So I'm very happy to be confident on the flow stuff. And for today, you'll just have to deal with me being not so confident. Okay. So I've broken this down into 3 theorems. Like I said, Bryant has theorems, I think A through to E. But here we've just got 3. I think it's enough. So this is the conformal Gauss map and the Bryant quartic. All right, so here's our notation. I'm going to try to explain as much as I can, and I'm going to try not to rush. But yeah, if anyone has any questions, please feel free to ask. Or yeah, if I mess something up. So here we've got as our basic object F. We're going to assume it's conformal. So this means that the coordinates are chosen so that the partial derivatives of F are orthogonal and have the same length, so that then the metric has a very standard representation. We're going to see all the formulae later. But this is not a big assumption because we have always the Willmore energy under control. So we don't worry about this making any further issues. And then we have this object associated with F, which I'm going to call Y, which is the conformal Gauss map. And I will define it and construct it in detail in the slides. And now the conformal Gauss map is going to allow us to define the dual surface, but the metric for that dual is going to only make sense. It's going to be non-degenerate on the set without umbilic points, because the coefficient of that, we will do the calculation, but the coefficient of that is going to be proportional to the trace-free second fundamental form squared. So when you have an umbilic point, it's 0. Okay. And really, this is quite impressive that it can be extended across. So you really have sort of a removability of singularities result embedded inside this work. I'm not focusing on that, but that is a necessary part of it. Okay, and so then the theorem is that on sigma star, which is the non-umbilic part of sigma, there's an equivalence between F being Willmore. So that means that the Willmore equation is satisfied at every point. So Laplace H plus H A0 squared equals 0. And the conformal Gauss map being, okay, in this de Sitter space, right? So here we have, this is sitting inside R41, right? So it has 5 components as a vector, and its metric is signature 1, 1, 1, 1, minus 1. Okay, so you subtract the last term in inner products. We're going to see calculations. And now this thing is space-like minimal surface. Okay, so we have this correspondence. Then we also have this quartic differential, QB, and it's defined in terms of the conformal Gauss map, like this. And it turns out it's global and holomorphic. And so, yeah, when you have a sphere, then these are 0. All right, let's keep going. Okay, second one. If you have a Willmore immersion that's not totally umbilic, okay, so totally umbilic here is really saying not a sphere. If it is a sphere, then everything is very trivial. We know what the energy is. There's nothing to do. And also we should think, how many things are umbilic? Well, how many umbilic points do we have? Well, if we have a topological sphere, so we have an immersed Willmore sphere, then there are necessarily umbilics. This is a nice thing to do in an introductory differential geometry subject. But if we have different topology, like if we're on torus or something else, and Bryant's theory does apply, except for at the end where we specialize to spheres, all of this works on with arbitrary topology. If we're on a torus or something, then we don't necessarily need umbilics, right? Anyway, then, yeah, so the whole, I don't know if this is the reason why Bryant did this, but at least it's a good reason in my understanding of it. We have this Lorentzian manifold, and if you look at the normal plane for the conformal Gauss map, then normal plane is going to be 2D, right? And so if I draw it in this way, then it's going to be just like the Minkowski plane, and you're going to have this light cone. Okay, and now the light cone in 2D is quite interesting because there's 2 parts to it. And it turns out that one part is going to correspond to the projection of the lift. Okay, so that's the original immersion. This square brackets is the projection back to R3. Project the original immersion F, and then but then you have this other direction, which is going to correspond to something called the Bryant dual. I think that's, or the conformal transform. I don't know if there's a standard name. Jan can correct me, but I've just called it Bryant dual throughout the talk.
I think it's fine to call it that way, yeah.
Yeah, cool. Um, and so this Bryant dual is, yeah, it has a very, very nice properties. Um, and the gives you this duality theorem, which is from the name of the paper, I suppose. Uh, it tells us that the umbilics don't make a big problem as long as it's not totally umbilic. But if it's totally umbilic, then um, it's a sphere and everything's easy. And we have that if the quartic differential form vanishes, then we can completely determine the transform as being a point, transforms to a point, constant. And then we also have in the other cases when it's not zero. So, for example, in a different topology, then you get this reflexivity property of the conformal transform of the Bryant dual. It turns into, so you have a branched conformal Willmore, and if you take the dual of the dual, you get back to the original surface. Okay, last one, the sphere theorem, and this is really the thing that we're going to be using for the flow. Actually, I'm not sure if this is kind of an interesting point for me. I don't know if this theory, as deep as it is, has an application for to study the flow in different topologies. It must, but I don't think it's been done. Someone might feel free to correct me, especially when this is on YouTube in the comments or something. um, okay, and then the last one is the sphere theorem. So here we've got sigma is the two sphere. And then when it's the two sphere, you have this very dramatic classification. Okay. So either you are totally umbilic, or we have the previous theorems, we have this quartic differential, and the conformal transform maps to this point Q in S3. And then you can stereographically project back to get a minimal surface that's complete with finite total curvature, and zero logarithmic growth, which implies planar ends. Okay, and that lets us quantize the Willmore energy, right? Because we can count the number of ends, and we know that there are at least two, because if there's just one, then it would be a sphere, again, once we compactify it. And so there's at least two ends, and so you can quantize the energy by 8 pi from below. So this implies that the Willmore energy is bigger than or equal to 8 pi. Okay, and so then just because I've been talking about the flow a lot, you can imagine that if you started a flow where the initial immersion, which is not a Willmore surface, just some smooth immersion, and it has Willmore energy less than 8 pi, the Willmore flow decreases this monotonically. So then you can never get back to a non-round Willmore immersion along the flow, right? This is really the main point for the flow. But all the rest of the theory is still extremely interesting, and you can see that this application really comes quite at the end. So you do need a lot of work. It's a big machine. It's a big result. Okay. So yeah, I'm going to try my best to introduce this the Bryant dual in a intuitive way. And I've got a lot of redundancy on these slides. So I've explained the same thing a few different times, hopefully using consistent notation. And if I find myself repeating, then I'll just skip through. But I've tried a few different approaches to understand this. A lot of it is because I'm myself just an amateur with this stuff, and I don't really know it very well. So that probably comes through in my presentation. Now, I've got this geometric miracle. I really like, so if you're one of my students, then you know that I like to call things miracles. Lots of things are mathematical miracles in my mind. And in this result, there are lots of miracles actually. But the biggest one, I think, is that, is the following. So I've written it on the slide, but I want to draw a picture. So if we take, let's imagine that we take a piece of a surface. Okay, so here I've got a piece of a surface. It's supposed to be 2D. Okay, and now I take, well, can I draw balls with this? Please let me draw balls. Probably not. Whatever. I don't want to break it. Maybe I can do. All right, I don't care. And now what we can do is we can take the value of the mean curvature along, for example, this dotted line, and we can draw the osculating sphere at that point. So osculating is tangential. That has the same mean curvature and is, tangential. So it's translated so that it's osculating well. And I'll just draw it. Okay, and it's just sitting there. And so this is SP. This is P. Let's call it P0. And then this black sphere is SP0. And we can roll this sphere along this dotted line, changing it as it goes so that it stays tangential and keeps the mean curvature of the surface. And so, we get this procession. Maybe they get bigger, maybe they get smaller. P0, P1, P2, P3, whatever, of mean curvature spheres. And so we get this map, we get this map that sends from each P to space of spheres. And there's one envelope, there's one really obvious envelope of this map, and that is the surface itself. So the original surface is an envelope of the family of mean curvature spheres. And the key geometric miracle, I think, is that there's a second one. That's very strange. So if you look at this picture, you might think, oh, there's obviously a second one because, there's this other curve down here. There's another sort of surface down here where there's also tangential to all the spheres and also has the mean curvature of all the spheres. But it's really not that obvious at all. If you think about it, it's one of those facts where if you keep thinking about it, you're less and less sure that it exists at all. And just to give you an idea of that, if we think now about curves, so let me just be for a moment in the Euclidean plane and we think about a curve. So let me draw a nice curve. And I really wish I had a circle tool, but I draw osculating circles. All right, so this one could have an osculating circle here. And then this one might be a bit smaller. Now these circles should probably be concentric. Oh, Glen can't draw to save his life because there's a thing called the Tate-Kneser theorem that says that convex monotone curvature curve segment has nested circles. Anyway, so you think about this family of nested circles, they don't have any smooth second envelope. of course, there's one envelope, which is the curve itself, but a second envelope, it doesn't exist. It's not, and if it does exist, it's not smooth, right? So if you had a curve that, changes sign on the curvature, then here you might have a circle that's there, and there you might have a circle that's there. But because the circles are concentric along arcs, the second envelope is a terrible object. It's not smooth. It's not nice at all. And there are a couple of papers written about this second envelope for curves, but it's just, I don't think it has any nice properties, and I'm not sure of any. There is a paper written. There are a couple of papers written about it, but I'm not sure of any good application of this notion. Whereas here, it's dramatically different, and I don't know how this happens, but it really is a miracle that there's a second envelope which is smooth. Anyway, okay, so let's talk a bit about some details. Here we're working in this Lorentzian space, R41. Okay, so it's R5, so everything has 5 components. And the notation I'm using is this inner product notation with a 4, 1. Hopefully I don't forget it. And yeah, we take the usual Euclidean product up to here, and then in the last term we subtract. Okay, the light cone, as usual, is the zero length vectors. Okay, so in this case, it really will be a cone, and it's level sets. So if you take the projection, it's level set. The quotient is going to be a sphere. That's all very standard. Now, there's a really important construction that sends points in R3, so vectors in R3, into this Lorentzian space. Okay, and it goes like this. So you put in the first 3 components x1, x2, x3, Glen. And then in the second 2, you do this alternating construction so that P of x is a null vector, right? So P of x is actually going to have 0 length. It'll be light-like. Okay, and we're going to use this quite a bit, this lift. Okay, so we can skip this slide. So I have a lot of slides in here that I wrote either for my own benefit when I'm learning, or if you want to review these later. This is just about why the right target is the Lorentzian space and not an S4, but I'll skip it. The next part here, okay, so now we're going to start doing some calculations. Yep. So this capital F is the lift of little f, right, which is our immersion. And we can work out some simple consequences of this formula, right? So if we take a derivative, this is di of big F. Okay, then we can calculate this easily, I hope. Everyone can calculate that. And then we can also calculate, okay, so if we take the pullback metric, does the pullback metric by the lift of capital F make sense? And that's what we're calculating here. So it would have these coefficients. And you can see that because these are the same, right? I and I, then if we take the inner product of Fi with Fj, then it would just be like Fj, Jj. And so they combine in this way, and we have this cancellation. And so you get a nice metric because we started with a nice metric. So that's good. Now, by construction, just from the calculation that we saw above, we already know that F has zero length, right? Because that's the way we constructed it. And we can also calculate that it's orthogonal to its derivative, right? This is just an explicit calculation. Just use the definition of the inner product and some algebra, and it's going to work very nicely. Okay, and I've got some Möbius geometry remark there, which you can take on faith. So yeah, the lift has all the information of the original immersion. You can see that easily. It's in the first three components. And the Möbius transformations act linearly on this de Sitter space, which is very good. Okay, so yeah, let's bring it together with the mean curvature spheres. We're going to define, now this is like in Bryant's paper, this is called, I think, E3. And it's like a lifted normal. It's not exactly the lifted normal, because if you used the lift formula, you wouldn't get this. But it is like the normal to the lift. It has unit length. That's good. So it's not a null vector. It's normal to the lift, and I mean it's normal to the position, and it's also a normal vector. So this is a good replacement for the normal to the lift. And what we do is we just take this on faith that it is a normal, and then we define y, which is our conformal Gauss map, to be the normal offset by the mean curvature times the position, right? So yeah, so I've written here, geometrically, y is the oriented round sphere tangent to the image. So it's tangent to F with the same mean curvature, right? And of course, yeah, if the mean curvature is zero, then you think of it having infinite radius. So it's a plane. We can calculate y squared in the this Lorentzian norm, and we get 1. So that's a nice calculation to do. All you need is the formulae that we've already derived. And so you can see that this maps into the sphere, which is good. That's what we want. All right, now we can do a lot of calculations to see, what are the consequences of this definition? Does it define something nice? Right, so what does it mean for y to pass through the projection of F? Well, it just means that y should be orthogonal to F in the 4-1 metric, the inner product. And you can calculate that pretty easily. So we just plug it in, the definition, and each of these terms vanishes independently. So we get 0. Now, to be a congruence, it should be tangential to F. So we can calculate that too. And by differentiating, just by plugging in the definition, right? Because y is hf, so that's this part, plus n, you get, again, 0. So it does satisfy, it is a second congruence. Yeah, and there's this little box on envelope condition, which I think is just saying the same thing again. Okay, so how do we relate the geometric information of the conformal Gauss map back to the original immersion F? Well, we just do it as you would if you were any kind of student of some submanifold isometric immersion subject, whatever. then you would start calculating. That's what you would do. And so we can do the same thing. We differentiate the definition to get the tangent vectors, which, okay, product rule, we can all do that. We use the Weingarten equation to simplify these. Now, there is a bit of calculation here, which I would like to show. Do I have it on the slide? No, I don't have it on the slide. So there is, yeah, it's not. Maybe I'll just give you the words for the calculation and have a go. And yeah, just like always, if you have trouble calculating through this, then feel free to reach out just ask questions on the Zulip. If you're too shy to ask on the general channel, just send me a direct message on the Zulip. That's totally fine. But this is very doable just from the definitions and using, the Weingarten equation. You can plug in the definition of N and the definition of F as lifts, right? So remember what they are as lifts. They are, N is this as a lift, and the F is this, right? And so you know already what's going to happen for the first three components, and you just have the last two to work out, right? And when you differentiate the big N, you're going to differentiate the nu. That's going to be your Weingarten equation. And then you're going to differentiate also the last two components. Okay, and then when you take the dot product with Fj, again, you can work out what that is. You're going to get some zero terms from those last two components, and you're going to end up with just minus Hij. This is the second fundamental form. And now for Ni and J, it's the same story. You're going to get some cancellation, and you'll see that you get the curvature squared, which is very nice. Yeah. Okay, and there's a little calculation down here. All right. So what I'd like to do in this slide is just combine the previous formulae to show what is the metric and what does it have to do with umbilicus, right? So we haven't seen any umbilic anything yet, but now we're going to. Okay, so we have this formula from before. And then if we take the inner product of yi with yj, right? So I've got some space here. So we can go hif plus hfi plus ni with the j, hjf plus hfj plus nj. Then what's going to happen? Well, F is orthogonal to itself because it's a null vector, and to Fj and to Nj. So this is equal to hfi plus ni hfj plus nj. And then you see that you generate all these four terms. Okay? And then with these four terms, you use the formulae that we just derived, which is why we did it. All right, no surprises. We set up the pins so that we can knock them down. Fi with Fj, right? That's Gij. That's the first term. Let's go down and have a look. Yep, that's the first term there. And now we've got these two terms, which are Fi with Nj multiplied by mean curvature. And okay, that's here, right? So we see we get second fundamental form each time. And the second fundamental form is symmetric. So we get two of it. That's fine. 2 times h. And then the last term, Ni with Nj, it's literally just here. We use this formula and we are done. Okay, so now we've got a little bit of a very simple argument to turn this into the trace-free norm squared. So first we recognize that the trace-free A0 Ij has this expression. And so we can write this entire right-hand side as the trace of A0 with itself. And then we use a 2D property. Actually, we've used 2D a lot, but here we use it again. If you have a trace-free symmetric tensor in 2D, then its eigenvalues are just like 1 and -1, whatever, 2 and -2, 0 and 0, whatever. And so when you trace like this, you get A squared, whatever that eigenvalue is, times the metric. And A squared, you can work out, is a half times the norm of A0 squared, because the norm of A0 squared is just A squared plus A squared. Okay, so you get this nice little expression, which I quite like here for the pullback by y of the metric, the flat metric in Lorentzian space 4, 1. And so you see straight away that if you have an umbilic point, then this is 0, and that's not good news. So a priori, this could have completely failed, right? If you were doing math research and you come across a thing like this, you might think, oh, this is really cool, but it could just be all nonsense. Like there might not be anything meaningful here. But it does work. But anyways, away from umbilics, it's nice. Okay, so yeah, I guess you can tell that I couldn't decide how to write A0 or not, h squared minus k or A0 squared, so often kept both of them in. But yeah, we can work out the rest of the geometry of the conformal Gauss map in this way. So we've got we've got the metric from the previous slide, and then we've got the area form, right? So it's going to be conformally invariant, which is quite nice. We've got the area of y is going to be related to the Willmore energy, right? So this is where it's nice to see h squared minus k, because then we've got the Willmore energy, which is integral of h squared. And then we have a topological piece, right? So this is just 2 pi times the Euler characteristic of sigma. So you see pretty clearly that if F is minimizing the Willmore energy, then it's not, I think this is just an intuitive reason, but so it's not that clear. But anyway, you could agree that it's possible that if F minimizes Willmore, then Y should minimize area. So you have this kind of heuristic correspondence already just from this algebraic manipulations. Okay, we've got the problem with umbilics, but apart from that, it looks like minimal for Y is Willmore in F. Okay, and this is just more talking in this box, this little meaning box. Okay, so now we did a lot of calculations using indices, but really what Bryant does is he's using local conformal coordinates. We haven't done that up to now, and he's doing them in the complex plane. And so what I would like to do now is very quickly revisit a lot of these calculations, but now in the conformal coordinates. So we're going to be seeing complex notation. We're going to be seeing Z derivatives and Z bar derivatives. Okay, and what does it mean to be locally conformal? It means this relation. So here lambda is the conformal factor, right? And it's a function. Okay, it's not a constant. Okay, and we've got this omega here, which is like the curvature, trace-free curvature, I suppose. Yeah, that's what we've got here. And then we have these formulae, which take quite a lot of work. And I'm going to give some details on the slides, but I put these here so that you can see where they're going. If you differentiate the Gauss map in Z and Z bar, then you get, this is the formula, this Willmore operator multiplied by F, the lift, of course, minus a piece, right? And this Willmore operator in the conformal coordinates looks like that, which might look a little bit foreign. It does to me, but it's not that foreign because HZZ bar is like the Laplacian, omega squared is like A0 squared, and H is H. So this is very, very close to already being convincing that this is this, but you have to check it, and I will show you the calculations. And so you get the Laplacian of y being Willmore plus this other term, okay, which is some kind of curvature squared times y. It comes from the area part. Okay. Yeah, what we want to conclude is that f is Willmore if and only if y is minimal. Okay, so I don't want to spend too long on these calculations, but I've put them in the slides and I'll at least display the slides. So if you want to work through them yourself, then you can, pause the video if you're watching the recording. If you're watching it live, then I'm going to go through quickly and do them yourself because I really do think that a lot of Bryant's work in this paper is algebraic, like crazy algebraic cancellations that just happen over and over again that are inevitable. And doing them yourself, I don't know, it's kind of a fun experience. I think it's great. It would make a nice honors subject. So we've already defined this n and we've already defined this capital F. So a lot of this is just revision, but the difference is that instead of doing Fi, Fj, whatever, we're working always with these conformal coordinates. Okay, so we can verify these from the definitions and we can verify all of these as well from the definitions. These are unit normal. We've already done this. This is that the normal is orthogonal to F. The normal is also normal to the surface generated by F. Okay, we've got already defined the conformal Gauss map. We've already shown that it takes values in this de Sitter space. So that's just revision. And now we get to our Willmore equation. Okay, so we've already defined this. Like I said, there's a bit of redundancy in the slides. And now we start expressing all the geometry related to F in terms of Z and Z bar derivatives and also the conformal factor. Okay, so we can calculate FZZ, we can calculate the Laplacian of F. This is an analog of the, Laplacian of F is mean curvature vector. Except, of course, you've got, so the beauty and also the beast of conformal coordinates is that your metric is always expressed in terms of this conformal factor. So this ZZ bar, this is a flat Laplacian, right? This is not your Laplace Beltrami. If you want it to be Laplace Beltrami, you should multiply by e to the minus 2 lambda, right? And so that's why the e to the plus 2 lambda is on the right-hand side. There's nothing crazy going on here. It's just bookkeeping, but with the new notation. Okay, so we can calculate also derivatives of nu with respect to Z and Z bar, and you get this equation down here. Keep going, you can calculate more derivatives of the lifts. And combine them together. You get these elements of the Hessian of F and the derivative of N. Okay. Yeah, there's a lot of redundancy defining this y over and over again. Because I guess it makes more sense to have the definition right here so you can see what yz is very obviously in yz bar. And we get in the complex notation, so we already calculated this before, which is why I'm going through it so quickly. This was just the calculation that showed that the induced metric is proportional to the trace-free second fundamental form squared times the original metric. And here we have the same thing. This is the trace-free second fundamental form squared. Okay, but this time we're doing it in the conformal coordinates. Okay, so it's a bit of repetition. It's good to do things twice, I think. And so we get this conformal space-like property because we have these two relations away from umbilics. So this is the umbilic set, the set where omega vanishes. Okay, we have to keep going because we need to take derivatives of the mean curvature, right? And so we just keep calculating and calculating. We get derivative of the trace-free second fundamental form in terms of the mean curvature. So this is actually from Caudazi. So if you were doing this with indices, then you would use the Caudazi, and this lets you see Caudazi in a very explicit way, which is quite beautiful. And just keep going, keep doing more derivatives, more calculations, and you will eventually get there, right? So here we finally get the Laplacian of y, and it has that form that we wrote in the beginning on that summary slide. And this one here, this is this Willmore operator, but of course in the complex notation. Okay, so here we're defining this just like before. And we can convert this back a posteriori, back to the, I don't know, more familiar, at least to me, notation of x's and y's. And we get this, which we recognize as the Euler-Lagrange operator of the Willmore energy. Okay. So yeah, sorry that was a little bit quick, but I think it was a lot of repetition, and the slides are there. So if you want to go through the calculations, it's good to check that you're familiar with the conformal coordinate in complex notation. Okay, so then there's some discussion here about why this second term is related to area. But it is, and I think I've already talked about this, so I'm going to skip it. But yeah, the slide's there if you want to read it. With umbilics, yeah, we also talked about umbilics. So in general, you will have umbilics, especially on a sphere, but maybe not on a torus or anything like that. And when you do have umbilics, the metric degenerates, and that's why when the quartic differential doesn't vanish, you get branched immersions. Right? We're going to, yeah, you really do need some kind of removability of singularities to get a global theorem, which does come out for spheres very nicely. Okay, so I'm going to stop soon. I feel like I didn't get very far, but I'll just maybe do a couple more slides. So the next part of this presentation is about the Bryant dual, which I kind of motivated before by drawing a picture and saying that it's the second congruence of mean curvature spheres. And then I also said something about light cones having two pieces, and it's the second piece. And so this is about that. So if we take the normal space in the de Sitter S31, then we get a plane, a real two-plane. And its signature, like as a metric space, is 1, 1. So it has a light cone, and it decomposes into two null lines. And if you look at one null line, you get the original F. And if you look at the second null line, you get another map, right? And so we can just call this map the projection of the second projection, the projection of the second null line is little f hat, right? And with that, we can take that as our definition, and that's going to be the Bryant dual or the conformal transform. It's like a rotation, but in a very loose sense. Okay, so it's not, definitely not a Möbius transform applied to the original immersion. And we can characterize it by it being light-like, right? Zero length. It is orthogonal to the conformal Gauss map and tangential to it. Okay, and of course, it's not equal to the original one. So yeah, I guess I wrote many times the same thing, but I really wanted to get the point across. It's very unexpected to me that you would have a sphere congruence and get two distinct useful envelopes out of it, but you do. Now, it's kind of important for, and I'll stop before I do this, but I just want to say what the next part is. It turns out that the transform of f at a point P is the unique point whose stereographic projection maps into from S3 into R3, which sends which goes back to F, whose mean curvature vanishes to second order. So that means that the mean curvature of P is 0 and the derivative of the mean curvature at P is 0. And so I do want to show those calculations, but I will do it next time. Yeah, so you've got mean curvature 0 and the derivative of mean curvature is 0. And that's really important for the calculations later. But okay, I think I talked too much and didn't do enough calculations, but yeah, thanks for your attention.
Thank you, Glenn. Thank you for a great presentation. It's a very difficult topic. It's a very difficult paper of Robert Bryant. It's very profound. There's lots of things in there, and I think you're doing a great job at, making it palatable. Yeah, you get a lot of applause, and you deserve it.
Thank you.
You're welcome. Are there any questions? And if there were one, how would it manifest itself? That's the
A question? I don't know. It
Yes.
could be a chat or something.
Would I see it appear, or would people just simply
Well,
speak?
yeah, feel free to talk. Maybe I'll stop sharing so that I can see the chat. Yeah, there's no chat. I don't see any chat. Oh, we have a lot of people here. That's great.
We do.
Wow.
We do.
Thanks
So
everyone for coming.
we're running out of time, so I will not ask questions at this point, but I want to make a comment. So you said the Bryant miracle. It really is, in fact, a miracle. And if I could, my understanding of this miracle is as follows, is really a manifestation of two things. The first thing is dimension 2. And in dimension 2, everything is locally conformally flat. So
Right. I should have mentioned that. Yeah.
that is something essential. In dimension 4, there is no equivalent of Robert Bryant's statement. There isn't even, as far as I know, a guess or anything similar. Also in dimension 2, the Laplace operator is conformally invariant in a sense. So it's the
Right.
right operator in the right dimension for this sort of miracle to manifest. And then, and this is probably more interesting for the crowd here, for the audience, is that Robert Bryant's result in dimension 2 is only true in codimension 1.
Right. I didn't mention that either. Yeah. Right.
And if you try to, a lot of it, you could extend to higher codimension, but then you hit a wall, a very clear wall that you see when you compute things,
Yeah.
and you can't go through what you've done today in higher codimension. So if I would invite those of you in the room who have never done it before to try to extend the first few slides of Glen to a higher codimension setup. So you can define this Y map, you can define this N map, and you can carry out the computation. And you will see after a few pages of computations that you hit a wall in higher codimension, and Robert Bryant's result is only true in codimension 1, as far as I know.
Yeah, yeah, absolutely. Those are great points, Jan. I think we've got to go, but
Yeah.
thanks everyone for your time and thanks for tuning in. And I hope I'll see you all in 2 weeks. I'll talk again, I guess.
Okay. See you then, Glenn. Cheers, everyone.
Bye.
Thanks, Glenn. See ya.
Bye.